Okay, so we're going to start with a quick review of what we did yesterday, and then we're going to talk about electromagnets, because electromagnets are going to be a part of the Chapter 20 homework set. So super fast review of what we said yesterday. This chapter is all about inducing voltage in a loop of wire that has no battery of its own. So to put it real simply, look, if I gave you, back when we were doing circuits, if I gave you this circuit and I said, okay, the resistance is 2 ohm, I want you to find the current, you would have been like, Spaldo, what's going on? Because what's missing in that diagram? Voltage. There's no voltage in that diagram, right? You use Ohm's law to figure out current. Delta V equals IR. So current would be the voltage over the resistance. So what we're going to learn in this chapter, it's possible to generate what we call an induced voltage in a circuit like this that has no battery of its own. Okay? Oh, and before I go any further, in this chapter, instead of delta V, they use the symbol E for voltage. You know, so E equals IR. Both of these equations are the same thing. It's just that E, you know, E comes from the term EMF. You'll probably see that at some point somewhere. EMF is the same as voltage, and what it stands for is electromotive force. Same thing as delta V, okay? Now, to do the problems in Chapter 20, it all starts with the topic of magnetic flux. So magnetic flux is this Greek letter phi, a circle with a capital I through it, and the equation for magnetic flux is BA cosine theta. B is the field, magnetic field. A is the area of the loop, you know. So here you would go length times length to get the area. And then cosine theta. Theta is the trickiest part. It's the angle between the normal line to the loop and the field. Okay, the normal line to the loop, it's like a line sticking perpendicular straight out of the loop. It's the angle between the normal line and the field. Now, is flux by itself very interesting? You know, and you may see that. Like, you could have a problem where it's like, calculate the magnetic flux, and just do it. But is that a very fun problem? No. When does magnetic flux become significant? It becomes significant whenever it changes. Whenever magnetic flux changes, that's when you're going to get what we call induced voltage, and then induced voltage leads to induced current. And then there's an equation for the induced voltage. To find induced voltage, you go N, which is the number of loops. You know, so here this would just be one loop, but if you have like copper wire that's been looped a bunch of times, like 1, 2, 3, 4, you know, N is the number of loops. You multiply that by the change in flux, and then divide by the time. Okay? Now, how many ways can you change the flux? 1, 2, 3. And in the homework set, you'll see all 3. The easiest way to think about it, guys, how do you find the change of something? Change of something is final minus initial. So just calculate the initial flux, the final flux, and take the difference, and that's the change of flux. Now, once you have this induced voltage, how do you get the induced current? With Ohm's law, you would just go I equals induced voltage over resistance. Okay? So that's pretty much what we did yesterday. Now, today, what we're going to talk about is how you would incorporate electromagnets into this chapter. So an electromagnet looks like this. Okay, I got this off the internet. It's a pretty spot-on diagram. I like it. So all an electromagnet is it's a wire that used to be nice and straight, right? It used to be nice and straight. It's a wire that's been coiled up. Just you take a straight wire, you go wrap, 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 and that's how you create an electromagnet. Now, what do we know about a long straight wire? So let's just look at a straight wire here, and we'll hook this up to a battery. Okay, so a straight wire, so let's look at like this region here. How does a magnetic field travel? So the current would be going like this, up like this. Current. So in this region that I marked off, what's the magnetic field doing? So you got to use which rule? Right hand rule number 2. Your thumb goes in the direction of the current, and then your forefingers curl, right? So what would the magnetic field be doing up here? Going in, so X's are in, and then down here it would be dots, right? So it's a circular path. The magnetic field would be a circular path. Now, what's going to happen to that magnetic field if we take that wire and instead of it being nice and straight, what if we coil it and we go wrap, 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 wrap? Will this wire still produce a magnetic field? Yeah. Is it going to be circular? No. The magnetic field of an electromagnet behaves like a bar magnet, like a permanent magnet. So back in chapter 19, I briefly mentioned bar magnets. You know, like you stick a picture of me. You guys all have photos of me on your fridge, right? Action shots. Like, Cam, how many photos of me do you have?
I think I have like 4 on my phone, and maybe I have like 10 on Facebook that I sent to Alex.
Cool. But you got some on your fridge?
Yeah.
Good. And you use a magnet for that. So, hey, a bar magnet. How does the magnetic field around a bar magnet, all bar magnets have a north end and a south end. The magnetic field goes like this. It comes out of the north, right? Magnetic field shoots out of the north and comes into the south. Okay, so these arrows represent the B, and then they loop around like this, right? And I showed you with my compass. That this is the case. Hey, what direction does a compass point in? Don't say north. In what direction does a compass point? In the direction of the magnetic field that it's in. So let me grab my permanent magnet and my super duper compass. So here's my super duper compass. Here is a permanent magnet right here. So look, I take my super duper compass and I put it next to the magnet. Can you guys see that? So which way is my compass pointing? Towards that back wall over there where all that artwork is hanging. So this side of the magnet right here must be the what? So the magnetic field is pointing that way out of this side of the magnet. So this would have to be the north. The magnetic field comes out of the north and travels around to the south. It's like this. So see now over here, the compass is pointing in, right? So the magnetic field's going in here and out there. Okay? So I'm showing you this because an electromagnet behaves in the same way. So look, let's look at this diagram of this electromagnet. So the current comes out like this, right? The current goes up like this. Now, either the magnetic field is going to be shooting in like this and then out like that, or it'll be doing the other way. Or it'll be going in like this and out like that. So how do we figure out which way the magnetic field is going to be going? Well, what you do is you use right-hand rule number 2, but you got to put yourself either on this end or this end. Why do you not want to be in the middle? Because in the middle, you're like this. You're like, is the current going that way or is the current going that way? You know, it's kind of too hard to tell. So put yourself at either end. So let's put ourselves over here on this end right here. So right here, looking at this point right there, which way is the current going? It's going like that. So do right-hand rule number 2. Which way are your 4 fingers curling inside the coil? Are they curling to the left or to the right? So you put yourself right here, right there. Put your thumb in the direction of the current. Curl your 4 fingers. Where are your 4 fingers curling? To the left. So this is telling us the magnetic field for this electromagnet is going to be going like this. right? And then like this over here. And then it loops around. It goes boom, and it loops around like this. Now, why is this important? Well, look, I'm going to show you. You are going to see electromagnet problems in the homework set. Now, I don't have an image for my computer. I have a demo set up over here, but it's not going to be very good for kids watching this at home. Basically, let me try to draw a picture. Let me revert this, and then I'll show you in class here. What you're going to see in the homework set is like this. Okay, so here's our electromagnet. Scoot this over. And you're going to have a coil of wire. So here's what you're going to see in the homework set. Look, you're going to have problems where you have this loop of wire with no battery. Okay, so here we have a loop with no battery. Is it possible to induce voltage in this loop over here that has no battery? Yeah. Okay, now what's the key idea with inducing voltage? You have to have a change in flux. Okay, so now how is this electromagnet going to become part of the problem? Well, look, let's add a switch. So you guys remember switches from circuitry? A switch is just a way to turn on or off a circuit. So if this switch is open, the electromagnet's off, right? So as soon as we close this switch, as soon as the switch is closed, what's going to happen? The magnetic field is going to what? Turn on. So then we went from having no flux. When the electromagnet was off, we had zero flux. We turned the electromagnet on, and now we have flux. Is that a change in flux? Yeah. So what that's going to do is it's going to induce a current in that coil with no battery. Do you guys follow this? So let me show you. In the time we have left, I'm going to end this lecture